are two rocket engines. In fact, they are both the same, SpaceX's Raptor engine. But how can that be? How is it even possible that this turned into this? And why did SpaceX even do it? And most importantly, what makes SpaceX's Raptor engine even possible? This is the story of how SpaceX turned the impossible into something operational. Welcome to the story of the SpaceX Starship Raptor engine. My name is Felix, welcome to What About It, let's dive right in. SpaceX has some pretty impossible goals for its future. Since its founding in 2002, they've had one vision they worked toward: to make humanity a multiplanetary species. To achieve their goal, they need to revolutionize rocketry as we know it and reduce the cost of spaceflight as much as possible. This is why SpaceX started the Starship program, intending to mass produce the world's largest rocket. SpaceX needs one key component that hasn't yet been created to achieve this: an extremely cheap, very powerful, and rapidly reusable rocket engine. To make it even more impossible, it needs to be mass producible. Something considered impossible by most rocket manufacturers today. Easy task. Raptor wasn't the first engine SpaceX ever developed. That honor goes to Merlin. When Merlin was first developed, it was a relatively small, weak, and inefficient engine. It could only produce 340 kilonewtons or 76,000 pounds of thrust and 261 seconds of specific impulse, which is a measure of efficiency. Despite all that, it had one thing going for it. It was simple, very simple. It may not look simple, being a bird's nest of wires and cables. However, because it wasn't aiming to be the most efficient or powerful engine, most of the components were much easier to produce. Since this was SpaceX's first main thruster, ease of production was key to making a working engine and keeping costs down. However, this was only the first version of Merlin. As SpaceX grew, it also gained the resources to improve Merlin while keeping simplicity and cost at the core of the design. Because of that, the Merlin 1D engine that SpaceX flies on their Falcon 9 rockets today is much more powerful and efficient, boasting an impressive 845 kilonewtons or 190,000 pounds of thrust and 348 seconds of specific impulse. For a rocket engine, that is the difference between a Mini Cooper and an F-150 Raptor. Still, it's the same engine, only improved over time. All of this was achieved thanks to SpaceX's iterative design process. But you can only iterate so much on a design until you reach a limit. Enter the beginning of the Raptor engine. Raptor was developed to power SpaceX's Starship rocket, a fully reusable super heavy lift rocket capable of delivering hundreds of tons to orbit on a single launch. SpaceX began developing Raptor in 2011 when it announced that it was working on an engine powered by methane instead of kerosene, which has been used in its previous Merlin engine. So it's been actively developing for almost 14 years now. The other key decision for Raptor was to make it a full-flow staged combustion cycle engine. In short, full-flow staged combustion is very hard to achieve, but it dramatically increases an engine's efficiency when done right. These two choices paved the way for Raptor to become the world's most advanced rocket engine. To understand SpaceX's decision, we need to break down some of the fundamentals of rocketry. In this case, how a rocket engine works. The idea behind a rocket engine is to push as much mass in the opposite direction as fast as possible. That sounds simple. Think of it as turning on a strong hose. Water will flow in one direction and the hose will want to go in the other. The more water flows and the faster, the more the hose will push against your arm. That is why firefighters are often seen holding a strong hose in teams. One way to achieve this concept on a rocket is to fill a tank with high-pressure gas and release it. Basically like a Mentos Cola rocket. The pressure from the tank will force the gas to exit rapidly, pushing the tank in the opposite direction. The only problem is this isn't very efficient. When it comes to rocketry, efficiency is everything, and one way to increase efficiency is to blow something up. Think about it. If your goal is to accelerate something quickly, what better way to do that than an explosion? When something explodes, it expands, rapidly increasing the pressure. If that pressure is confined to a small area, we can force that high pressure out on the other end. Translating that to a rocket engine means we don't need to have any high pressure tanks to hold and release gases. Instead, we can take those tanks and fill them with combustible material. Great. The difficulty lies in controlling that explosion. Last time I checked, explosions weren't exactly known for being controllable. The other problem is how to add more explosives to something actively exploding. The key is pretty simple in theory. It is pressure. To pump more fuel and oxidizer into an active explosion, that fuel and oxidizer have to be at a higher pressure than the explosion. If you want to achieve that with tank pressure, well, at that point you don't even need the explosion. So let's try pumping it. Okay, that didn't work. Pumps need to be seriously powerful to pump something into an active explosion. Raptor's current combustion chamber pressure is at about 300 bar, or 4,351 pounds of force per square inch. In an engine the size of Raptor, having an electric pump big enough to supply the chamber with more propellant would make the engine extremely heavy. Not to mention the batteries to operate a pump of that size would add even more weight. So instead of using a regular pump, rocket engines use what are known as turbo pumps. These work by igniting a small amount of the rocket's propellant to spin a turbine which pumps the propellant at an extremely high pressure. So rocket-powered pumps, nice. That comes with one slight problem though, temperature. If a rocket engine were to use the perfect amount of fuel and oxidizer to operate the turbo pump, the temperature would quickly rise and melt the whole assembly. That's why turbopumps are purposefully inefficient. They typically pump extra fuel or oxidizer into the chamber to cool it. The less efficient the combustion, the lower the temperature you'll end up with. However, once the propellant has run the turbopump on most rockets, it is dumped overboard, reducing the overall efficiency of the rocket. It is wasted. It's even called a waste gate on SpaceX's Merlin engine. This is what's called an open cycle engine. These are the simplest rocket engines out there, which explains why SpaceX's first engine uses this cycle. It's easy to build. I mean, easy for a rocket engine. But what it lacks in efficiency, it makes up in simplicity. The less complicated an engine is, the more reliable it'll run. However, the Raptor engine must be efficient if SpaceX wants to get to Mars. That is why SpaceX chose to use a full-flow staged combustion cycle engine instead of an open cycle. It was the first successful engine of its kind and was first used during the Starhopper test flights. But what does this mean and why does it matter? Today I want to thank Surfshark for sponsoring yet another Why episode and for protecting your online activity. We talk about safety a lot at Why. After all, it's a top priority in spaceflight. Whenever lives are at stake, special precautions are a must. So why not do the same? After all, we spend so much time online that it has become a big part of our lives already. Surfshark is an easy, no-hassle solution to keep your data private and your browsing secure. So why do you need a VPN? Simple. It creates a private network for you, blocking prying eyes and shielding you from data breaches, hackers, and other criminals who try to access your info. They are everywhere. You deserve privacy. Here comes the best part. Surfshark is extremely easy to use. It even has a built-in antivirus protecting you from hostile threats like data worms and Trojan horses. Don't know what those are? Don't worry, that's the best part. Surfshark takes care of it for you. You don't need to know. What about a more dangerous environment like public Wi-Fi? Surfshark's got your back. Proxy emails and instant alerts shield you, and if anything's compromised, it can even give you a fresh start. You can use it on as many devices as you like with one license. Surfshark protects your entire household with one license. Everyone in your family is protected. Safety isn't just important in spaceflight. Set a new standard for your own life. Go to surfshark.com/Felix for 4 extra months of Surfshark at an unbeatable price. The link is in the description and in the pinned comment. Surfshark, surf with your own set of rules. Instead of just one turbopump, SpaceX's Raptor has 2. One runs by burning more oxygen and the other by burning more methane than needed. So that's the closed cycle, no waste. And because it burns the fuel twice, first in the pumps and then in the main chamber, it's called a staged combustion cycle. In fact, in Raptor, all of the liquid methane and liquid oxygen used in the engine flows through these pre-burners. And that's where the full flow part of the name comes from. This is part of the reason Raptor is so revolutionary. Not a single drop of propellant is lost by being thrown overboard. So if it's so great, why was SpaceX's Raptor the first rocket engine to be able to use it successfully? Some areas are much harder to find details on, as SpaceX doesn't exactly want to share how they've managed to accomplish such a feat. However, the biggest difficulty SpaceX needed to overcome with Raptor was temperature. Hot, 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 hot. SpaceX wants to maximize its efficiency, and to do this, it needs as much pressure as possible. The only problem with that is that high pressure brings even higher temperatures. Despite what it seems, the highest pressure and temperatures aren't at the end of the rocket engine, but at the start, specifically near the pre-burners. In fact, the current version of Raptor, Raptor 2, has a main chamber pressure of around 300 bar, but its pre-burners can reach up to 600. Fortunately, SpaceX does have a trick up its sleeves. Its employees are likely the world's most advanced metallurgists. They've developed materials with exotic names like SX500 and many other secret alloys to solve these high-pressure, high-temperature problems inside the engine. But in rocket engine development, there's always another problem. These pre-burners get so hot and have so much corrosive oxygen that even the world's most advanced metals would quickly melt. So even with some of the world's most exotic materials at hand, SpaceX still needed a way to keep these pre-burners from melting and disintegrating. Unfortunately, the exact method by which SpaceX does this is a closely guarded secret, but we can infer a few things from the information we have. Active cooling in the turbopumps is undoubtedly a part of it. It is likely SpaceX runs the cryogenic liquid oxygen and liquid methane through small channels around the turbopumps, allowing them to cool the metal while heating the propellants. Something similar is done on the engine bell, not just on Raptors but on many rocket engines. Another technique is something called film cooling. This is where a small amount of relatively cool oxygen or methane is pumped into the chambers along the edge, providing a small thin layer of cooler propellant to act as a shield. One thing that isn't speculation though is the fuel type. Remember, Raptor is fueled by liquid methane, the same stuff that may power your kitchen stove or your heater. Ever went camping and cooked some sausages on Starship fuel? There's another secret reason why SpaceX chose this fuel. While most other liquid-fueled rocket engines use either RP1, refined kerosene for its simplicity and ease of use, or liquefied hydrogen for its efficiency, Raptor uses methane for its relatively average characteristics. Compared to the other two most commonly used fuels, methane is almost perfectly balanced between them when it comes to trade-offs. It is more efficient than RP1 while remaining much simpler to use than hydrogen. However, this is just the tip of the iceberg. Starship is intended to operate in ways that no other rocket has ever even dreamed of, such as being fully reusable and being able to refuel on another planet. Needing to refuel on another planet immediately ruled out RP1, as there is no kerosene on Mars, and RP1 leaves a soot that builds up over time, making reuse much more difficult. So that leaves hydrogen. Its extremely high efficiency, its ability to be generated on Mars, and the fact that the exhaust from a hydrogen engine is literally water, meaning no soot, make it seem like an extremely good option. However, there is a glaring problem. Hydrogen is extremely difficult to work with. SpaceX's Raptor is already the most advanced engine ever made, and adding hydrogen would likely make it even more desirable. However, hydrogen has one problem. It is incredibly light. But wait, isn't light great for a rocket? Technically, yes, but hydrogen is light because its atoms are so thin. It's the smallest atom known to us. One positively charged proton is in the middle and one negatively charged electron circles it. That's it. It's tiny, so tiny that even storing it becomes a hassle. Have you ever heard of a gas that is so thin that it can sift through solid steel? Welcome to the world of hydrogen. Overall, hydrogen seems like a good option. However, its drawbacks are fairly severe. It would require significant changes to Starship's design philosophy, which could jeopardize its reusability. This left only methane, which, while not the most efficient, is one of the easiest to handle, has a very clean exhaust, making it easy to reuse, and most importantly, it can be produced on Mars. But all this is still just a part of what makes SpaceX's Raptor unique. This brings us to the most crucial thing about Raptor, its ability to grow. As mentioned earlier, many rocket engines are updated over time. However, the Raptor takes this to a whole other level. It was designed from the beginning to evolve, and not just by a little bit. The very first version of Raptor had a thrust of around 185 tons and weighed over 2,000 kilograms. Raptor 2 then increased that thrust by nearly 50 tons to 230, reduced the engine mass by 400 kilograms, and impressively reduced the commodity hardware needed to operate the engine on the vehicle's inside by 1,000 kilograms. Then Raptor 3 came along to baffle the world of experts. It was so unbelievable when SpaceX first showed it to the world that the CEO of United Launch Alliance, Tory Bruno himself, thought SpaceX tried to fool everyone with the first released pictures. This couldn't possibly be the entire engine. It almost looked like SpaceX had stripped it of all its outer components. But they didn't. This was it in its fully operational form. Raptor 3 increased thrust yet again by around 50 tons, now sporting a total thrust output of 280 tons, nearly 30% more than the first version. It also reduced the engine's weight by another 100 kilograms, while the vehicle side hardware decreased by another 1,000 kilograms to just 1,700. However, above all else, Raptor 3 was simple. It looked so incredibly sleek that the world couldn't believe it. All of the changes don't show the true scale of how slimmed down Raptor has become. It looks like a skeleton now compared to the original Raptor. So what made this possible? One design philosophy.
The best part is no part. The best process is no process.
This has taken Raptor from this to this. This isn't just a visual change. Removing unneeded components reduces the number of failure points. After all, if a part is missing entirely, it can't break. This also allows SpaceX to get rid of parts that may not have been able to withstand the high temperatures and pressures that SpaceX's Raptor has to endure. It also reduces the need for protective systems for those components. A good example of this is the environment outside the engine. Yep, Raptor doesn't just face heat on the inside. Looking at the other versions of Raptor, you can see it's a rat's nest of cables, and some of those cables need to stay at precise temperatures and could easily be damaged by something like a fire. I like to call Raptor 1 the flying spaghetti monster. And last I checked, rocket engines are not exactly known for avoiding fire, especially SpaceX's rocket engines. They must endure fire from within and fire on the outside when returning from space. Raptor 3 has an active cooling jacket implemented throughout the engine. Small channels are crafted into each outward-facing engine part to cool it down actively during re-entry. But SpaceX hasn't just gotten rid of parts, they've combined them, deciding to integrate multiple components into single areas or pipes. The number of flanges decreased greatly as well. So much so that Musk stated in an interview with the Everyday Astronaut that SpaceX will have to cut the engines up if repairs are needed inside. This can counterintuitively decrease the price further. Even though it can sometimes increase complexity, the reduced individual part count often makes up for it. Other revolutionary technologies have also assisted in this from outside the rocket industry. Metal 3D printing, which Raptor utilizes extensively, allows it to integrate multiple components into one. It makes the cooling jacket possible in the first place. Although Raptor is already the world's most advanced engine by an extremely wide margin, it's still quite a bit away from what it must be to achieve SpaceX's goal of becoming multiplanetary. While Raptor was being developed around 2016, Musk announced that the production goal for Raptor was a specific impulse of around 382 seconds and a thrust of 310 metric tons. In other words, despite Raptor 3's improvements over Raptor 2, it's still around 30 seconds and 30 tons away from its initial goals. Looking at the leaps between Raptor 1 and 2 and then between 2 and 3, SpaceX will likely reach this goal. However, they are beginning to run into some fundamental laws of physics, as the efficiency they are pulling from this methane-powered engine is already approaching a point where it can't be improved much further. If there's one thing that can be said about SpaceX, it's that they have a knack for turning the impossible into late. While SpaceX may not achieve this in the next year or two, it will likely become a reality eventually. That's what differentiates Raptor from many other rocket engines. It was designed to be iterated on from the beginning. Its entire development cycle is highly flexible, and it doesn't shy away from scrapping one idea and trying another. And it is still growing. That's it for today. Remember to smash that like button, subscribe for more. This is what fuels the algorithm. This is how you can help us for free. Check out our epic shirts in your favorite Space Nerd store. A new Raptor design and our brand new Starship Block 2 design are both up. The perfect gift link is in the description and in the card you should see now. Also check out our print store at shop.whataboutit.space to buy a picture for your favorite wall. A significant amount of every purchase goes directly to our photographers, and if you want to train your space IQ even further, watch this video next to continue your journey. Thank you very much for watching, and I'll see you again in the next episode.